We're very happy to have Yuval Paris for his second talk in this workshop. And he'll be talking about trace reconstruction for deletion channels.
All right, well, good morning. So I want to tell you about maybe the problem I've been most obsessed about the last few years and last couple of years. And despite all this obsession, the problem is mostly open, but I'll tell you what we know and what we believe. So actually, there are 3 relevant papers I will survey, one with Fedi and Nazarov, one with Alex Zhai, and there's a third one I'll come to later with Nina Holden and Robin Pimantel. OK, so what is the question? So I'll describe it in a communication framework, but it actually arose in several different applications in math biology, in statistics, in learning theory. But let's first describe a communication framework. So we have a sequence of bits, x, that say Alice wants to send to Bob, an n-bit string. So she transmits the bits one by one. Each bit gets deleted with the same fixed probability q. For much of the talk, you can think of q equals a half, but in general, q could be anything between 0 and 1. It's not a function of n. Now, Bob receives the compressed string. So he doesn't know, for each bit he receives, he doesn't know where it came from. His goal is to reconstruct the original sequence exactly with high probability. So of course, he can't do it from one such output. So Alice keeps sending the same original string again and again until there's enough information for Bob to reconstruct the original string. Okay? So each time that she sends it to this channel, of course, the deletions happen independently. And so the question is how many samples are needed? These samples are called traces. How many traces are needed before Bob can reconstruct the original string with probability 90%, say, or any fixed probability, no matter what the original string was? So as we'll see, the problem changes its nature if the original string is restricted. For instance, if it's picked at random, that makes the problem easier, though still not easy, but easier. The hardest case is when you don't know anything about the original string. It could be arbitrary. OK, so as I'm emphasizing, we'll focus on 2 kind of problems. The worst case x, when the x is arbitrary, that's the most important and fascinating question, I think. And we have some progress on that, but we don't know. And then we have a lot of progress on the average case or random case where x is chosen at random. And I'll tell you more as we move on. So, so this problem arose in many different contexts. And usually, it's not the real application. So for instance, in the biological context, you have many, we have lots of descendants of some individuals, say Genghis Khan, and say these descendants are not closely related to each other, except through this connection far back. And you want, from their DNAs, to reconstruct the original DNA of this ancient individual. So, of course, what DNA undergoes is not just deletions. Even there are portions of mitochondrial DNA which aren't affected by both parents, only by one parent. But still, there are also other kinds of mutations. But certainly, deletions occur. So if we cannot understand what to do with deletions, obviously, we won't solve the harder DNA reconstruction problem. And there's applications in sensor networks and so on. So the problem goes back more than 20 years, but in this exact form, it goes back to 2004, to this paper, Batu et al. And they observed, I'll show you closely, that you certainly, to construct general strings, you certainly need at least n. Now, there's a closely related problem, which at first looks a lot easier, which is hypothesis testing, or deciding between two original strings. So in the problem, as I stated, x, the unknown string, was arbitrary. Could be anything. So you had to decide between 2 to the n options. And, but suppose I tell you it's, x has two possibilities, two possible strings, and just decide between these two strings. It looks easier. It certainly is easier. But it turns out it's not that different. So I'll just sketch why, and we'll come back to this point later. So suppose I had an algorithm that with t samples will tell apart with probability 3/4, say, whether the original string is x0 or x1, some two options. And it can do it for any two distinct options, okay? I want from that to get an algorithm that will reconstruct the string. And right now, I'm just worried about the number of samples. I'm not worried about running time at all, okay? So what I could do is, for any two specific strings, if in t samples I can decide with probability 3/4 which is the right one, then by taking 100 nt samples, I can make that same decision with a high degree of confidence. Because if I have 100 nt samples, I'll divide them into blocks of length t. In each one, I'll decide with and I'll be correct with probability 3/4, and I'll just do a majority vote, and we'll have some concentration, which means the probability I will, if with t samples I can do it with probability 3/4, with 100 nt samples I can do it where the probability of error is tiny, exponentially small. And then I can deal with the union bound over all pairs of strings and really decide what is the original string. So just by losing a factor of constant n, I'm going to be able to convert the hypothesis testing problem to the full reconstruction problem. And as we'll see, for the reconstruction problem, it's open whether t is even polynomial. So losing a factor of n is not going to change the answer, is it polynomial in n or not? So the two problems are closely related. And I'll come back to this point more slowly later. OK, so so one first question, so if I focus about distinguishing between two strings, say x and x prime, the first intuition would be that the strings that are hard to distinguish would be strings that only change in one location. But this intuition is wrong. So such pairs can be distinguished in order n samples because of using the test of the Hamming weight. So, so if two strings differ in one bit, they have different Hamming weight by 1. And then, so Hamming weight just the number of ones. So if I apply the deletion channel, I'm going to get different distributions of the Hamming weight. Either it's binomial with k and q, with k and p, or binomial with k minus 1 and p. And these two binomial distributions can be distinguished in order n samples just by computing mean and variance. So the test you will do is look at 100 n samples, look at the Hamming weight, average, and compare. And so look at the average and see, is it closer to what I expect from x or from x prime? And just by looking at the standard deviation, you can see that this kind of test will be decisive. So that's one observation. So if there are strings that are very hard to distinguish and, say, need more than polynomial number of samples, they must actually be different in many places. And we don't know if that happens. But that's the hard cases when they're different in many places. So although over the years, I talked to many other people who studied this problem. There are not that many papers on it because it's been hard to make progress. One notable one is by Hollenstein, Mitzemacher, Panigrahi, and Wieder from 2008. And what they proved is an e to the root n upper bound. You see, the trivial upper bound is exponential. That's very easy to. For instance, if you wait exponential time, there will be one time with no deletions, and you're done. But already this is a non-trivial bound, exponential of root n. And they also had an intriguing result that said if the deletion probability is small enough, say less than 1%, then they could do it in polynomial number of samples. But only in the random case. So for a random string, if the deletion probability was low enough, then they had an argument which was polynomial. We'll see that both of these results we're going to improve, but that's kind of the benchmark before the current works.
And that result is with high probability in terms of the initial string?
For the random, yes. Yeah. So in the worst case, we have a result with Fedi and Nazarov, and let me say that the same result was obtained independently at the same time by De, O'Donnell, and Servedion. Both were published in the same conference. This is for worst case x. We improve the e to the root n to e to the cube root of n. So now this, both these e to the root n bound and the e to the cube root n bound were obtained by the same basic algorithm, which is linear tests. So you look at the output, you look at actually a single location in the output, and you average all the samples in this one single location, and you use that to distinguish two strings. I'll be more precise, but it's basically a linear test looking at averages of outputs. And so that was used in both these papers, and now we've reached the limit of this technique of linear tests. That is, both of these papers show that e to the cube root n is sufficient, but also necessary for reconstruction using linear tests. So if we want to improve that, we have to use nonlinear tests. And there's no reason to believe that linear are optimal, just linear are more easy to analyze. And one new result, I'll come to a newer result later. So with Alex Zhai in late 2017, we showed that if the deletion probability is less than a half, then we can construct a random string, so with high probability in the input, in e to the root log n traces. So this improves on this result in pushing the boundary from 1% to a half, and pushing the number of samples down from polynomial to subpolynomial, namely e to the root log n. And in the end of the talk, I'll mention a more recent improvement of this, joint with Nina Holden and Robin Pimentel, where we drop this restriction in q less than half. So now we know for all q in the random case, and we improve the e to the root log n to e to the cube root log n. And I'll say why that's some natural boundary. So I'll come to that improved result later. But a half is a meaningful value here because a half is the limit where a certain kind of greedy algorithm can work in the reconstruction. Please stop me if there are any questions or anything unclear. OK, so let's warm up by seeing some easy lower bound that in the worst case, we need at least n observations. And this is just to distinguish these two strings, x and x prime. So x is half zeros, half ones. X prime is the same, except the boundary has been shifted by one spot. So these two look quite similar. And in the outputs, the output are always going to be a string of zeros followed by a string of ones. The only difference is the distribution, the length of the string of zeros. The total length is the same, has the same distribution in both cases. And the length of the output of zeros will be, in this case, binomial n over 2 and p, and in this case, binomial n over 2 plus 1 and p. And these two distributions are very close in total variation. Their total variation distance is 1 over root n, and really, we know that the sufficient statistics, the best thing to do would be just to average the lengths from many samples. And then, again, an easy calculation with mean and variance tells you that you need n observations to distinguish these two cases. So this is a standard, like basic statistics exercise to distinguish samples from these two distributions. So basically, you use maximum likelihood, and you see that you need order n to distinguish. One can also ask about lower bounds for the random case, and there you see this n lower bound is for the worst case, because these kind of strings are quite special. They're not going to typically occur. And for the random case, the best lower bound is log squared of n. So, okay, so let's talk about this linear reconstruction in the worst case. So I'm going to now go to the proof of my result with Nazarov of e to the cube root n. And anyone here who does combinatorics, I hope, will enjoy this, because it's really a classic use of generating functions with the twist from complex analysis. So to simplify the notation, I'm going to focus on the case q equals half. But again, except for notational differences, the proof is the same for general q. OK, so one thing you might try is, well, let's just look at the first bit of the output. And the first bit of the output indeed has different expectation if you start from x and x prime, because the expectation of the first bit, say y0, is just the input bit written in binary, right? Because y0 with probability half, it's x0. With probability 1/4, it's x1, and so on. So you just get, in the expectation of y0, you see the input written in binary. So this means that if you just look at the first bit and average enough times, you'll be able to read off the input. But unfortunately, this enough is exponential. So, because in order to get to the far bits here, you have to wait for an event of probability, 1 over 2 to the k to happen. So it's easy to see this will be exponential. Particularly if x and x prime agree in the beginning, first k digits, then the difference of the expectation is only 2 to the minus k. So, of course, you can also do similar things from the end, but that won't change. OK, now, it turns out that the radical improvement occurs if we look at any bit in the output, not just the initial bit, but we adapt. This bit will be adaptive. So for any pair x and x prime, there will be a potentially different bit we will use to distinguish them. And then we have to somehow combine all these tests. So let's look, what's the expectation of the jth bit in the output? So y is the output coming from x. Okay? This is easy to write down. So the jth bit in the output will come from the kth bit in the input for some k, which is at least j. And what's the probability that xk will yield yj? Well, first of all, xk itself must survive. So this is the probability half here. And then before xk, we have k bits, because we're starting from 0. So x0 to xk minus 1. And of these k bits, exactly j have to be retained. So this is binomial distribution, 1 over 2 to the k, k to the j. So this is the expectation of yj, just written as a linear. So every bit in the output in expectation is just a linear combination of the input bits. Now, when you see this formula, this suggests generating functions. So take this expectation, multiply by w to the j, where w is a complex number, and sum this over all j. So if you do that, so you take this, you multiply by w to the j, and you sum over j. Then you change the order of summation and use the Newton binomial formula, and you get to this form. Okay, so this is an exercise with binomial expansion. Again, you take this, multiply by w to the j, sum over j, and then you're going to sum over j this expression. And this is sum over k, sum over j. So when you change the order, you sum over j inside, you just get the binomial expansion of this. Okay? So, but now this is somehow neater than that, because this relates to generating functions in the things we care about. So here are y's the output, and here are the x's the input. And these are two polynomials, one in the variable w and one in a new variable w plus 1 over 2 that we will call z. Okay, so we're relating these two generating functions. Now, to get information from this, we really want both w and z to be in absolute value near 1. Because, for instance, if w in absolute value is very small, then only the first few coefficients matter here. And if it's very large, only the last. And similarly, if z, so w plus 1 over 2, is very big or very small, we're not going to really be looking at the whole sequence. So both w and z should be in absolute value near 1 for this to really be informative. And that really means that w and z should both be near the point 1 in the complex plane, because the mapping z goes to z plus 1 over 2. OK, it maps, maybe I'll draw this. So it maps the unit. So maybe I'll write. So we're going to use z equals w plus 1 over 2. In other words, w is 2z minus 1. And just as a preview, we're going to use this formula when z is on the unit circle. So this is the unit circle where z is. We're going to vary z on the standard unit circle around the origin. And when z varies on the unit circle, w is going to vary on a circle of twice the radius, of radius 2, around the point minus 1. Okay? So, and despite my picture, these two circles are actually tangent here. And that will be important. In fact, this tangency is what yields the improvement from e to the root n to e to the cube root n, you see. OK, so this is repeating this identity we wrote down before. And the goal, so now think of the hypothesis testing problem. So there are x and x prime. Later, we'll combine them again to get the reconstruction problem. There are candidates x and x prime that we want to separate. We're going to look at the outputs. And we're going to use this identity. So our first goal will be to find a number w. So by small, I just mean near 1, about 1 in absolute value. So find a w which is about 1, so that these two series are going to be different. So when these two series differ, it means that one of their coefficients must differ, and that will be our tool to distinguish them. So again, we have this change of variables. Z is w plus 1 over 2. And when we compare the power series, so this cy notation is a little confusing because y here is averaged over. So this is just really depends on x rather than on y. So this is the series coming from x. This is the series coming from x prime. And they're equal to this expression, right? So again, this cy is defined this way, so it's already an expectation. Note, so y has been averaged over. So our goal will be to find a small z. Actually, z will be on the unit circle, so that this expression is large. So once we find that, then we'll say if the right-hand side is large and the left-hand side, which is the same, is also large, which then will mean that some coefficient in the left-hand side has to be large. So if you write this left-hand side as the sum of expectation yj, w to j, one of these coefficients has to be significant. And then we will use that coefficient in a statistical test to average over that location in the output. So we'll see how this happens. But again, in order to make the next step, we want to know that this series is going to be not too small for some z on the, and we'll do it for z on the unit circle. So if we have a polynomial, this polynomial by definition is not the zero polynomial, so it can't vanish on any interval. But what we need is a quantitative version of that statement, and this is a theorem of Borwein and Erdely from '97 that says the following. If you have any series with a, okay, what we'll use it is when the coefficients are 0 plus minus 1, but it's more generally works if, say, the first coefficient is 1 and the next are all less than 1 in absolute value. For any polynomial like this, and no matter how high is the degree, if we have an arc of the unit circle, then the maximum of the polynomial cannot be too small. Namely, there is a point z on the arc where the absolute value of f of z is at least exponentially e to the minus cl. So remind you, the length of the interval is 1 over L. Okay, so this is this Borwein-Erdely inequality. And okay, I won't. So the proof involves a nice bit of complex analysis, even though it's from '97. You know, it could have been done earlier. But let me just prove something a little bit weaker, namely that let's check that the beta, which is the maximum over the arc of f of z. So let me take an arc here, and I'll make this arc go, instead of length 1 over L, let me make it 2 pi over L like this, just for change the constant, it doesn't really matter. And then let's max over this arc gamma f of z, call that beta. And then let me prove something a little weaker that already gives the idea, so n to the minus L. This was known long before. This is more elementary, and it won't much affect our main result if we use this instead. So why is this true? Given little f, define capital F by rotating little f. So product f of z e to the I times 2 pi j over L. Product j from 0 to L minus 1. Okay, so what are we doing? We're taking the function f and rotating the argument by
What is the n more about?
sorry. So
The degree of the polynomial.
yes. Okay, so as I said, in the end, in the sharp bound, n doesn't enter. So the sharp bound is uniform in n. And this bound is indeed optimal. But this bound, which you can think of this as, right, this is the same as e to the minus L log n. And if we were to use that in the main theorem, instead of e to the cube root of n, we would get e to the cube root of n log n. So it's not that different. Anyway, given little f, you define capital F like this by rotating the argument, and then this capital F is still a polynomial. And f of 0 is 1, absolute value. But if you look for any z on the unit circle, I can bound above f of z by just bounding the factors. So each of these factors is at most n, because if I look at little f, it's just bounded by n on the unit circle. Okay? So I'm going to get n times, and there's one factor which is beta, because no matter what z I start with, if I look at all these rotations, one of these rotations will fall in this special arc gamma. And on that arc, we defined the maximum to be beta. Right? So we see that we can bound over the whole unit circle, we can bound f by beta times n to the l minus 1. Okay, now we use the maximum principle, which says that for an analytic function, in particular for a polynomial, its maximum on the unit disk is attained in the boundary. So because the value at the origin is 1, means there must be some point on the boundary where the value is at least 1. And this means, so in other words, this maximum has to be bigger. This is an upper bound for the maximum on the circle. So n to the l minus 1 beta has to be bigger than 1, which means beta is bigger than even n to the 1 minus l. So we can even gain an extra n there. Okay, but with a little more complex analysis, one can improve this to the e to the minus l. Okay, so how are we going to apply this theorem? So first, observe that I made the condition here a0 equals 1 and all the rest are less than 1. But it's the same if I say that the first non-zero coefficient is 1 and all the later ones are less equal 1. So if I take this such a polynomial and multiply it, because if I had that situation, I could just take out some power of z and reduce to this case. Okay? So again, I can weaken the assumptions here. Instead of assuming that the coefficient a0 is 1 and all the rest are less than 1, I can just assume the first non-zero coefficient is 1 and all the later ones are less than 1 in absolute value. And you reduce to this case just by taking out the power of z. So that strengthened version we can apply to this function. So this is the difference between our two candidates. And then we deduce that, so there is some point z in this arc of length 1 over L or constant over L, where f of z is bigger than e to the minus CL. And this means, because of the identity, that these psi y of w and psi y of prime of w will differ by e to the minus CL, where w is related to z as written there. So w is 2z minus 1. So now we're going to fix z. Before was a variable. Now we're going to fix a choice of z where the inequality holds, and then fix w to be this 2z minus 1. So they're stopping to vary. They're going to be just these fixed numbers from now on. So we're going to, now how big is w? So here is where the tangency gets used. So z is going to be on an arc close to 1. So we can write z as e to the I theta, where theta in absolute value is less than 1 over L. And then because of the tangency, what this means is that if you move a small angle theta, w is outside, but it's not growing very fast. It's growing quadratically in theta. So that's where the tangency comes from. And of course, you can also just, this formula is simple enough. You can just use basic trigonometry to verify this. So w is 1 plus order 1 over L squared. But you'll see now, so you see that this 2 came from the tangency. As you see, this 2 will directly lead to the result of the 1/3. Okay? Again, stop me if there are any questions. So again, because of the identity and this Borwein-Erdely theorem, we got that there is, for any two strings x and x prime, the corresponding outputs y and y prime will satisfy this inequality for a suitable w. Again, the choice of w depends on this pair x and x prime. And we get this inequality. Now, remember, w was less than, had this form 1 plus order 1 over L squared, which is less than e to the 1 over L squared. So if I take any power of w and this power is less than n, I can bound this by e to the constant n over L squared. Okay, again, we use the fact that this is bounded by e to the 1 over L squared. Take this to any power less than n, it's at most e to the constant n over L squared. So therefore, if we move it to the other side, we see that there has to be some j where this difference is bigger than e to the minus cl times e to the minus cn over L squared. And we're losing 1 over n because we're replacing the sum by a max. Yes?
It doesn't matter, but I don't see why you need to lose the 1 over n. You can just do the statistical test on the sum of yj.
No, but then you lose it because the variance will be larger. So it won't, it doesn't improve things. It will be the same. It will be equivalent. But here it's just, it gets to be more elementary because we're going to be doing the Chernoff bound on random bits rather than bigger random variables. So it's more elementary. As far as the result, it is exactly the same this way or that. Okay. So okay, so there is some j where this happens, and the 1 over, and now when you see this expression, it's a lower bound, so we want to optimize it, and the optimum is by equating these two terms, and that's where L equals cube root of n comes in. So if you take L, which is cube root of n, this becomes e to the minus 2c cube root of n, and then the 1 over n can just be swallowed by changing the constant. So we conclude that there is some location where the means differ by e to the minus cube root of n. And now, to distinguish x and x prime, we will just average on that location. And it's just another very basic statistics question. We have two distributions on a random bit. Their means differ by some epsilon. How many samples do you need to distinguish them? Well, 1 over epsilon squared, which is also e to the cube root of n. So formally, if you take t, which is e to the suitable constant cube root of n samples, then the chance to distinguish, this chance of choosing wrongly between x and x prime is going to be, this is what the Chernoff bound or Hoeffding inequality gives you. It's if you have the means differ by epsilon, the test you will use is look at the empirical mean and choose x or x prime according to which of the means of expectation yj or expectation y of j prime is closer to the empirical mean. So for any x and x prime, choose, to be concrete, choose the first j where this inequality holds, and then use that coordinate to distinguish. And now,
if you want to do this algorithmically, is it difficult to get this j?
I'll say something about that. So, so this is right now not yet algorithmic, and the point is that this probability is so small because it's going, with this choice of t, what you get here is still e to the minus constant. So what you get in the exponent is exponential in cube root of n. So this, if you multiply this by 2 to the n, it doesn't hurt it at all. So you can, or even 4 to the n. So you can use this for reconstruction as well, because you can afford the union bound between all pairs. So again, if you're not worried about running time, only about samples, then you can look at all possible pairs, do all these tests, and the chance that any of the tests will come out wrong is still exponentially small, or better than that. Okay. So here is so I promise I didn't pay off Remco to ask the question about the running time. It's a natural question. And there is so for those of you who know something about linear programming, there is a way to do this quickly. Now, what does quickly mean? We still have to look at e to the cube root n samples. So, so the complexity is at least the sample complexity, at least the number of samples. But before it was exponential in n. So it's enough. Really, the painful part is just looking at all the samples and computing these averages. Once you do that, the rest is polynomial time. And the basic idea is to reconstruct the bits one by one, the bits of the input. So, so suppose I've reconstructed the bits up to x0 to xm minus 1. And now I want to reconstruct the next bit, xm. So I say, well, what could xm be? It could be either 0 or 1. So I consider these two possibilities separately. Now, so I fixed, these are known, and say I fix xm equals 0. Then I think of all the remaining x's, I make them continuous variables in the unit interval. And we'll see how that will come in. And I'm going to look at the conditions I have. So what I need is that the expected input in the jth location should be close to the empirical average up to this e to the minus CL. So with this L, which is the cube root of n. So because I took enough samples, if I have the right choice, then all these inequalities will be satisfied. But if I have the wrong choice, then the Borwein-Erdely theorem will tell me that I cannot satisfy all these inequalities. And that remains true even if I make x. So let me say this again. In the positive case, if I chose xm equals 0 correctly, then I can satisfy all these inequalities with just putting in the correct choices of the remaining x's. So discrete values, 0 or 1. But if I made the wrong choice for xm, so if I chose 0 when the true thing should be 1, then Borwein-Erdely tells me that I cannot make these inequalities be satisfied for any choice of x's, even if I choose x's to be in the continuous unit interval. And I define these EYJs formally by this identity. Okay? So that, again, follows from this Borwein-Erdely theorem. So in other words, I have two linear programs. One of them is feasible, one is infeasible, and I can decide this in polynomial time. So there are polynomial time algorithms for linear programming, and I just have to do this n times. Okay, I don't have, sorry?
This transition between verifying pair by pair and going to a polynomial algorithm is specific to this algorithm that used to
Yes.
root of n, or?
Rigorously, yes. In principle, we believe that in these cases, always the running time will be essentially bounded by n times the sample complexity. We don't have a general proof of that. OK, I have to skip the complex analysis proof of the Borwein-Erdely theorem. But I want to say that the Borwein-Erdely theorem is sharp. And this implies that, as is shown in these two papers, mine with Nazarov and the other one I mentioned, that there are two strings x and x prime that where in all the output bits they differ only by e to the minus cube root of n in expectation. So it means if you want to distinguish between this x and x prime using these kind of linear tests, you really need this many samples. Now it would be nice to see what these x and x prime are for large n, but we cannot. Because the proof that they exist is a non-constructive proof by a pigeonhole argument and some analysis. And so we know that there exist just pairs x, x prime, but we can't look at them, unfortunately. So in the last 10 minutes, I'll tell you about the reconstruction of random strings, which is so this involves much harder proofs, hence I'll be much quicker in discussing them. So first, for the case q less than half, there is we're going to go bit by bit, and the key thing will be to align an output to an input. So the reconstruction problem is hard because given a location in the output, we don't know where it came from in the input. If we knew exactly where these came from, it would be a much easier problem. So if we can align with some precision, so if we can look at a bit in the output and say, well, this approximately comes from here, this can really help us in the reconstruction. And the idea is for q less than half, we can do nice alignment via the greedy algorithm. So let me explain that. So this is an example of an input string, and the gray arrows represent what happened in the deletion channel. Okay? Now, unfortunately, the algorithm doesn't know this. It just has an output, but it now has a part of an input. So remember, what we want to do is reconstruct the input bit by bit. And the first bit is actually very easy. So the problem is, as you get deeper, the reconstruction gets harder. So suppose we got to some, we constructed some m initial bits, and we want to reconstruct the next bit. So we have a partial input, and we have an output, and we'd like to align them together. So what we could try is just greedy guessing. So say, this one, where could it come from? Well, the first place it could come from is this one. This 0, it can't come from here because there's a 1 here in the partial input I already know. So the earliest place it could come from here. So you see here the greedy algorithm made a mistake. But it made a guess. It's possible. And then now the greedy algorithm, although it made a mistake, it now realigned to the correct location in the next step, and so on. Okay? So to understand how the red and gray arrows differ, we have to take a perspective of a random walk. So when we go from the original string to the output, we compress by a factor p. So p is 1 minus q. P is the retention probability. So if every bit is retained with probability p, we compress with probability p. In other words, to go from the output back to the input, we have to expand by a factor 1 over p. So it means if I'm running at speed 1 on the output, and I look at the gray arrows, at what speed are they moving on the input? They're moving at speed 1 over p. Okay, speed bigger than 1. So as I'm running here, 1, 2, 3, these are running at average speed 1 over p. Now, what about the red arrows? How are they running? So first of all, they are always constrained. They're always going to be before the gray arrows. But when they are strictly before the gray arrow, I claim they move faster. So to understand that, just think, if I have a string, if I just write down some arbitrary string of bits, B1, B2, B3, and so on up to bk, and now I'm looking for this string inside a random string. So suppose this is a random string, but this b is not related in any way to x. So I just write down a b, and now I take, so b is arbitrary, x is random, and I want to find b as a subsequence of x. How far do I need to go in x? Can anyone tell me? Typically. 2k, right? Because each bit, each bi, the number of steps I have to wait for it is geometric with parameter 1/2. So it has mean 2. I have a bit in a random string. It will occur in expectation after 2 steps. And so so after about x 2k, with some error 1 plus little o of 1, in location 2k is going to be enough to find this string. So when the greedy algorithm is wrong, it is looking for bits in the wrong place. it will still find them. But when it's looking in the wrong place, the red arrow will move at speed 2 because it's looking for a string just in an independent location. So it will meet in speed 2. So if we think of the green and of the gray and red arrows, when they separate, then the red one, which is earlier here, it is running faster than the gray one, so it will catch it. And it can never separate it by more than log n, because a biased random walk, if you have a random walk that's biased towards 0, it will never get further than log n from 0 in n steps. Yes? So, sorry? So Q is the deletion probability, which is less than a half. P is the retention probability, which is bigger than half. Yes?
If you replace the greedy with blocks, you can get paper and a half.
You can, with blocks. So,
Greedy looking for the max. Oh, because
so in fact, we will replace behavior blocks, but we won't be looking for exact matches. We'll be looking for correlations in blocks. But indeed, so once we have this alignment, then there is a further story using generating functions to complete the work. And just like we had exponential in cube root of n, here we'll get exponential in a power of log n once we get this alignment within log n. And I don't have time for this more precise story. Once we get the alignment, what to do. So I'm going to skip this and just tell you about the improvement. So sorry about that. So just last summer, with Nina Holden and Robin Pimentel, we proved this, as I mentioned, for all Q between 0 and 1, and we actually improved the complexity also to e to the cube root log n. And this improvement is already the best one can do without improving the worst case, because every string of length n contains all strings of length log n, if you use, say, base 2 plus epsilon in the log. So, so what this means, if you had a better algorithm with less than e to the cube root log n, it would imply a better algorithm for the worst case reconstruction, better than e to the cube root n. So this is not a likely way to obtain a better algorithm for the worst case. So really, to make further progress, one has to do something about the worst case problem. We've pushed this to the limit. But just to give you the idea, the formal paper that appeared in Stock for the worst case, where I gave you the full proof, this was a 5-page paper. And actually, the Stock publisher wrote to me, "Are you sure you sent us the whole paper? Because you have 14 pages and you're only using 5 of them." But I assured them that was the whole paper. While this one is, there are 2 papers. One is 25 pages and the other one is 35 pages. And so the random case involves a lot of estimates. And in the last 3 minutes, I can just give you one idea. So how do we do the alignment when the greedy algorithm fails? Actually, for about 6 months, I thought that when the greedy algorithm fails, maybe there's a phase transition and maybe the problem really gets much harder when Q is bigger than a half. But it's true that the greedy algorithm fails, but there are other algorithms based on correlation. So it turns out when you optimize, the right kind of test is, so the optimal test is to divide the string into blocks of length log to the 5/3 n. And again, this is the only power that works. If you use anything else, you'll get a worst estimate. So, so maybe not the first thing you would guess. And you take this block W and try to locate it in the output. So in the output, this should map to a block of length p times, shorter by a factor p. And we want to see is, for each candidate, again, we have some partial reconstructed string. And we want to see, for the last section of it, where does it correspond to in a given output. So we have candidate windows in the output, and we want to see, do they correspond to this W? And we divide W and W tilde to log n blocks. so equally sized blocks. And the kind of correlation test we do is for each of these sub blocks in the window, we compare, is its majority vote the same as this one? Okay, so for each of the blocks, we go one by one on the blocks here and one by one on the blocks here and compare the majority votes for each of these blocks. And if W tilde really came from W, then we expect these majority votes on the sub-blocks to be correlated, because there's a lots of bits that are just being copied. So this creates some correlation between the majorities. And then if a lot of them, so then this is like a recursive order 2 majority. Then we look at is the overall, so we look at the number of blocks with the same majority and ask, is this bigger than half the blocks or not? If it's bigger than half by some margin, then we declare, yes, it looks like W tilde really came from W. And this is the method we use for alignment. Now, because we're working exactly at the boundary of possibility, there are actually a lot of, the estimates get very delicate. So actually a lot of our traces, even if we choose correctly, the test may fail, because the deletions may create asynchronize these input and output blocks. So it turns out that by using this test is very picky, very selective. It will throw out many of the traces which are good, but we have enough. We have e to the large constant cube root log n, and it turns out that this test will still keep enough of the traces, and it will. So all we need is that the number of false positives is going to be substantially smaller than the number of true positives. And after we do that, so we do this with all strings of W tilde, and then whenever we have a fit here, we can deduce an alignment of order log n with probability, which is 1 minus exponential log cubed n. So then there is a further improvement by a second refined alignment step. To see more, it's all on the archive, and I'm here for a couple more days for anyone who wants to discuss. But what I would be most excited by is any new ideas for what to do with the worst case strings. I just want one more remark, is that even for random strings, if you use linear tests, we can show you still need this huge number, e to the cube root n samples. So the linear tests, we know for random strings, the linear tests are really not telling you the truth. Because the pigeonhole argument still works for random strings. So it's natural to suspect that even in the worst case, you can do better than linear tests. But I really don't know what is the guess. Is it polynomial or not for the worst case? On odd days, I think this. On even days, I think the other way. So I really don't have a good conjecture on that. Thanks for your attention.